Okay, welcome to Level 1 Science Online with Henny van Vuren.
Hi, Year 11s. Welcome to another lesson here. I hope that everything goes great with you guys and that everybody is safe. Um, yeah, we need to continue because we are still going to write our test in week 8. So it means we have a little bit more than about 2.5 weeks to get through everything and make sure that you guys have everything that you need to do really well. Okay, so last time I saw you, we worked on the beginning of acid and base reactions and neutralization. So we'll continue that today and look at some of the past questions. Alright, so without further ado, here we go. Okay, so here we go. So first of all, you see an atom in a metal oxide. Another name for a metal oxide is simply a base, and this of course is a Bohr's reaction. Okay, atom in a metal hydroxide. So remember, when you see an oxide or a hydroxide, you are going to say Bohr's. Then when you see carbonate or even hydrogen carbonate, you're going to say quarks. So let's have a look at this top. Okay, let's try this again because I probably just recorded about 25 minutes without recording, so that wasn't awesome. Anyways, so we learn. So a student wanted to make a neutral salt, and the salt's name is sodium nitrate. So they give us the salt. So we know that it's going to be sodium nitrate. Okay, and they're going to make sodium nitrate by mixing sodium carbonate and nitric acid. Ooh, I saw the word carbonate. Sodium carbonate. Carbonate is a quarks reaction. A carbonate plus an acid gives us water plus a carbon dioxide plus a salt. Now, nitric acid. Okay. Explain how litmus paper could be used during the process to show the salt being produced is neutral. And when we hear the word neutral, we know pH is 7. And when the pH is 7, the H pluses plus the OH minuses will give us water. And they will be in equal concentration. Okay, so we have now carbonate, which is sodium carbonate, plus nitric acid. Okay, so you're going to take the sodium carbonate and you're going to make a solution of the sodium carbonate. And then you're going to add nitric acid to the sodium carbonate. But you would probably have a universal indicator in there so that you can see when it turns green. Now, to confirm that it's green, and if you wanted to use litmus paper, you know that in a neutral situation, red litmus paper will remain red and blue litmus paper will remain blue. So you have to test with both of them. Okay, and it's going to give us sodium nitrate, which is our salt, because the carbonate and the acid, the hydrogen part of the acids, gives us the water, gives us water plus carbon dioxide. Now this was a bit of a tricky question because how are they going to make these salts? Now you have a solution of sodium nitrate water and the carbon dioxide just boiled out. So we will then heat this solution until all the water evaporates and then we only have sodium nitrate left. As I say, that was a bit of a nasty one, but yeah. Okay. Really hope you can't hear my screaming kids in the background there. Alrighty, let's look at the model answer there. So, how to make it? Mix the two solutions together, then make the resulting solution. Put in evaporating dish, could be heated using a leftover. Huh? Okay, that's how to evaporate it. But anyways, you add in universal indicator to it, add a base, it will turn green when it's neutralized. Heat to remove, the sodium nitrate will remain. And the solution will be neutral when the red and blue litmus paper both remain the same color. We said all of that. Then another achieved point, they asked us to write down the word equation for sodium carbonate plus nitric acid, but they told us that it's going to form sodium nitrate salts. Okay, so we have that already. But so sodium carbonate plus nitric acid gives us, remember it's quarks, it gives us water plus carbon dioxide plus, and the salt, remember the carbonate and the hydrogen from the acid forms the water and the carbon dioxide. So what's left is the nitric acid and the sodium. Sodium nitrate. Okay, there you go. That's the word equation, and we just got achieved. Now we can write a balanced symbol equation. So the first thing is we need to translate this all into the symbols. So sodium and carbonate. Sodium, look, there it is. And carbonate. CO3. Now sodium carbonate is 2 minus and sodium is 1 plus. Can you see that? Okay, so 2 minus and 1 plus. So we need 2 of these to cancel out the 2 negatives there. Okay, there's our molecule. Plus nitric acid, which you were supposed to know off by heart. But if it's an acid, it has to give off an H. And we know that hydrogen is 1 plus. And nitric acid is going to be nitrate, which is NO3 minus. And that's a 1 minus. Aha! It's a match made in heaven. So it's a 1-to-1 relationship, whereas this one is a 2-to-1 relationship. Okay, so the carbonate plus the acid gives us water plus carbon dioxide plus the salt. And we said that the salt is sodium nitrate. Sodium, as we know, is Na. And nitrate, as we know from up here, is NO3 minus. Okay, so why did I put a plus there? N, no man, yep, O3. 1 minus and 1 plus, so it's a 1-to-1 relationship. Excellent. So you have just achieved merit. Let's have a look at this. So let's start with the sodiums. How many sodiums on this side? There's 2. And how many sodiums on this side? Only 1. How do I fix it? I put a 2 in front of my whole molecule. Remember, now we have 2 sodiums and 2 nitrates. We'll get to that later. So sodiums are hunky-dory. Now the carbonate. So carbon, how many on this side? 1. How many on this side? 1. Ching, ching. How many oxygens? Now remember the carbonate. So a carbonate always stays together. Okay? The same with SO4 and so forth. So these guys, they always run together. Okay. Anyways, so how many hydrogens on this side? There's one. How many hydrogens on this side? Two. How do we fix that? We put a 2 in front of it. Now we have 2 hydrogens and 2 hydrogens. Boom, boom. Oxygens we have 3, and there's 1, 2, 3. And now our nitrate, NO3, there's 2 of them, because remember this 2 counts on this whole molecule, so there's 2 NO3s. How many NO3s on this side? 2 times NO3. Yay! You've just achieved excellence. Easy peasy. Okay, write the word equation and a balanced symbol equation for the reaction between sulfuric acid and sodium hydroxide. Oh, this is so easy. Okay, so sulfuric acid. Now, you're supposed to know that sulfuric acid, so let's write the word equation first. Sulfuric acid plus sodium hydroxide. Yay! Sodium hydroxide. I see the word hydroxide. What do I immediately write? Bores. Okay? Will give us water and a salt. Water. Now, hydroxide, the hydroxide side, sodium goes into the water, and the acid, the hydrogen part of that, goes into the water. So we have sulfur remaining and sodium. So sulfur, sodium, no, that doesn't sound right. Sodium sulfate. Okay, there's our word, and we just got achieved. Now, sulfuric acid, you were supposed to study this. It's H2SO4. But let's say you forgot, so you know an acid always gives you a hydrogen, and sulfuric is the sulfide over here, or sorry, the sulfate, not the sulfide. We usually in this don't use the sulfide, okay? So SO4, now look at it, SO4 up here is 2 minus. Hydrogen over here is 1 plus. So how many hydrogens do we need to cancel out the 2 minus? We need 2 of them. H2SO4 plus sodium hydroxide. So sodium is Na1 plus, and hydroxide is OH1 minus. That is a 1 plus and a 1 minus. That's a 1-to-1 relationship. That is a match made in heaven. You don't have to add any numbers. So we know it's going to give us water, because we know about Bohr's. Base plus acid is water and salt. And then the salt is going to be, we said the hydrogen, remember it's sodium sulfate. The hydrogen and the hydroxide is used to make water. So we now have sodium and sulfate. Okay, so sodium and sulfate. Let's just check them if they are electrically balanced. So sulfate, SO4, is 2 minus, and sodium, as you can see there, is 1. How many sodiums at 1 plus do we need to cancel out the 2 minus? We need 2 of them. Okay, so by doing that, you've just achieved merit. Now we're going for excellence to balance this guy. So, hydrogen, how many on this side? 1 and 2. And how many on this side? There's 2. Yay! Now, oxygen. Now, remember I told you that when you have sulfide, just like your carbonate, and your sulfide and your nitrate, they always stay together. Okay, sulfite, nitrate, they don't break up. So this sulfite, how many do we have on this side? Only one. How many do we have on this side? Only one. Okay, that's good. So the sulfates, sorry, are balanced. Now, how many sodiums on this side? There's one. How many sodiums on this side? Ooh, there's two. How do I fix that? I put a 2 there. But now by putting a 2 there, it changes my oxygens and my hydroxides. You see that? But these are sorted again. So now we have to step back and just do my hydroxides and my hydrogens again. So 2 sodiums and 2 hydroxides. So how many oxygens? We have 1, 2. Okay. So if I put a 2 in front here, I now have 2 oxygens. And by putting that 2 in front there, I also have 2 hydrogens plus the 2 hydrogens from here. It gives me 2 times 2 is 4 hydrogens, so they are balanced. There you go. You just achieved excellence. Easy. Okay. Awesome. In 2013, a student carried out an experiment in the lab using the following method. Step 1. The universal indicator was added to a solution of hydrochloric acid in a beaker. Step 2. Calcium hydroxide. The moment you see hydroxide, you say is Bose. Was slowly added until the solution turned yellow and then green. Oh, yellow. What is the pH of yellow? It's going to be pH of 5 to 6. And what's your relationship between your hydrogens and your hydroxides there? There's still more hydrogens in comparison to hydroxides, but it's getting much closer to each other, isn't it? And green, the pH is 7. And the hydrogen concentration is equal to the hydroxide concentration, which means that H plus OH minus gives us H2O. Okay. Step 4, the contents of the beaker were then poured into an evaporating dish and left in a sunny place for days. So they are trying to isolate the salt. Remember, because a base plus an acid gives you water and a salt. They want to isolate the salt. This is the same as the previous year's experiment. The contents of the beaker were then poured. Okay. Explain the purpose of each step and how the equipment and chemicals used to achieve this. So firstly, you put the hydrochloric acid in a beaker over here. You then add your universal indicator and then slowly add your base to start neutralizing it. And you need to talk about the pH. You need to talk about how the hydrogen and hydroxide ions. And then lastly, you evaporate the water away to give you the purified salt. So there's your model answer. So show it's neutral, that it's green. The contents are put into an evaporating dish so that the water can evaporate and leave the salt, calcium chloride. How did they get to calcium chloride? Well, look, it was calcium hydroxide and hydrochloric acid. Calcium hydroxide. So the hydroxide on this side and the hydrogen from the acid will bind together to give you water. So what is left, you have chlorine and calcium, and that gives you the calcium chloride. Okay. So now it's a different experiment. The following method was used. Step 1, a beaker was placed on a balance, as shown in the diagram. Step 2, hydrochloric acid was added to the solid sodium carbonate. You see carbonate and you say corks. Step 3, the mass was recorded over time. Write a word equation and a balanced swimble equation for the reaction between hydrochloric acid and sodium carbonate. So, they gave us, right, let's use corks. So, sodium carbonate plus hydrochloric acid gives us water plus carbon dioxide plus, now we have to figure out the salt. So the carbonate is going to go into the carbon dioxide, and the oxygen that is left from that is going to become the hydrochloric, so it goes with the hydroxide to form the water. So we have chlorine and sodium left. Sodium, is it chlorine sodium or sodium chlorine? Sodium chloride. Okay, so sodium carbonate is Na, and look, it's Na1 plus. Carbonate we know is CO3 2 minus, and you will have this table, but it will not have the names on it, so you need to recognize carbonate as CO3 2 minus. So it's going to be CO3, but it's a 2 minus, and sodium is a 1 plus. So how many 1 pluses do we need to cancel out the 2 minuses? We need 2 of them. Plus hydrochloric acid. You studied that, hopefully, HCl. But if you didn't, hydro is hydrogen, 1 plus. Chlorine is 1 negative. It's a 1-to-1 relationship. There you go. That gives us water. You know what water is. Plus CO2 plus sodium chloride. Oh, sodium and chlorine. Oh, look at that. Plus 1 minus 1. Match made in heaven. Now let's count them. Sodium, how many on this side? There's 2. Oh my goodness. And there's only 1 on this side, so let's put a 2 in front there. Now remember, the carbonate becomes CO2, and so we can say there's 1 carbon, there's another carbon, there's 2 oxygens, 3 oxygens, and that's the 3 oxygens that sit over there. Okay. Hydrogens, how many hydrogens on this side? There's only 1. There's 2 over here, so let's put a 2 in front there. Now chlorines, how many chlorines on this side? There's 2 chlorines. How many chlorines on this side? Oh, that 2 works on that chlorine as well. So we have 2. Yay! It's balanced. And you just got your E. Okay. Easy. And then experiment 2, explain why the mass of the beaker and the contents would decrease over time. In your answer, state any observations that would be made as hydrochloric reacts with sodium carbonate. Explain how the products formed by the reaction lead to a decrease in the mass of the beaker and content. Let's think about this. Okay, corks. Come on, pen. Corks is a carbonate plus an acid, gives us a water plus carbon dioxide and salt. Carbon dioxide, okay, carbon dioxide. What happens to the carbon dioxide? What do you see? Bubbles! Yay, bubbles! And what happens to the bubbles? They go out. And the carbon dioxide is released into the atmosphere. La 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 la. That carbon and oxygen had a mass. So the water and the sulfur stays behind, but not the carbon dioxide. And if that gas, even though it's a gas, it still has mass. It's going to make the whole system lighter and lighter as time goes on. Okay, the mass will decrease and decrease until there's no longer any sodium carbonate, or they have neutralized each other completely. Okay, so that's what you're going to say. So state their observations, made the hydrochloric acid reacts with the sodium carbonate. So what you saw that the sodium carbonate was disappearing. You saw bubbles forming, and you know that was the CO2. If there was universal indicator in there, you would have seen the color changes happening. And then explain how the products formed by the reaction lead to the decrease in mass of the beaker and the contents over time. But it will stop eventually. Okay, let's look at the model answer. So observation is fizzing will be observed. The fizzing observed is due to the carbon dioxide gas being released, and therefore because the carbon dioxide gas is leaving the beaker, there's less mass remaining in the beaker, and therefore the balance measures less mass or less weight. So write a word equation and a balanced symbol equation for the reaction between sulfuric acid and potassium hydroxide. Sulfuric acid, you should know this, H2SO4. So that is the word equation. Okay, sorry. Sulfuric acid plus potassium hydroxide. Potassium. Please ignore my spelling. Hydroxide. Gives us, it's a hydroxide, so it's a Bohr's reaction. Water and the salt, which is going to be what? So the hydrogen from the sulfuric acid, the acid part is the hydrogen, plus the hydroxide from potassium hydroxide forms the water. So what's left? Sulfuric and potassium. Potassium sulfate. Okay, let's do our balanced symbol equation. So you studied sulfuric acid, you know that it's H2SO4. Even if you didn't, H you know is a 1 plus and SO4 is a 2 minus. So we need two hydrogens to cancel out the 2 minus from the SO4 plus potassium hydroxide. So potassium we know is K and it's a single, plus, and hydroxide is a OH minus, but it's a single, so it's a 1-to-1 relationship. Okay, and that gives us, we said, water and potassium sulfate. So H2O plus potassium, which is K, and sulfate, which is SO4. However, sulfate is 2 minus, and potassium is only 1 plus. So how many potassiums do we need? 2. There we go. Now, that's merit. Now we need to balance it. So, how many hydrogens on this side? There is 2 and 3. How many on this side? Uh-oh, 2. How are we going to fix that? I don't know. Let's leave it for later. Okay. Let's start then with potassium. See, that's why I told you to always write Bohr's. And what did I write? Acid plus base as water and salt. But just showing you that you can still get there. So if it's like 2 and 3, don't worry about it for now. Let's start with the base. So potassium, how many on this side? 1. How many on this side? 2. So we put a 2 in front. Now we have 2 potassiums and 2 potassiums. Brilliant. How many hydroxides? There's 2 of them. That means there's 2 oxygens. And how many oxygens on this side? Oh, only 1. Let's put it 2 there. Now there's 2 oxygens. 2 oxygens. How many hydrogens here? 2. 2 times that gives us 2. Uh-oh, but this side we have 2 times 2 is 4. There's the other 2. Bang. Yippee! Okay, now sulfates. There's 1 sulfate on this side and 1 sulfate on this side. So that's balanced. And just like that, you got your excellence. That is wrong. They needed a 2 there. Okay, so we'll stop there for today, and I'll give you a few practice things to do, and then we'll do some more tomorrow. Okay guys, thank you very much for your time, and thanks for your attention. And I know it's not always easy to learn online, but yeah, and remember you can pause and rewind these videos. That's why I make them. Okay, so have a great day. Look after yourself. If you need me, reach out to me. We'll take it from there. Okay guys, thank you. Bye.